I would like to describe our research with regard to simultaneous PET MRI that can measure extracellular pH in the tumor microenvironment. I don't have financial interests or relationships to declare with regard to this work. Tumor acidosis is a consequence of glycolytic metabolism that converts pyruvate to lactic acid, which is then secreted from the tumor cell. Tumor acidosis, low pH in the extracellular microenvironment below 7.0, can be used for diagnosis and also for evaluations of treatment. We use an agent initially inspired by Dr. Silvio Ame and his colleagues at the University of Torino that has a sulfonamide that is pH dependent and therefore has a R1 relaxivity of this agent that is high at low pH and low at high pH due to the protonaceous state of the sulfonamide. So if a PET instrument is well calibrated, where the PET radioactivity that is detected is correlated to a dose calibrator very carefully, and if you know the initial ratio of gadolinium to a radionuclide agent, well, then you can use PET imaging to actually measure gadolinium within a sample. We use this then to use a gadolinium and gallium-based agent that are co-incubated within the same phantom, and we can measure the change in R1 relaxation rate due to the MRI agent. We can measure the activity from the PET agent, and with the decay-corrected ratio of gadolinium to gallium at the beginning of the study, we can then convert to gadolinium concentration and measure little R1, the T1 relaxivity of this agent, which is correlated to pH as shown by this sigmoidal calibration that we have reproduced from the work from Dr. Ame. Unfortunately, the error in PET MRI is largely on the MRI side. We have a large amount of gadolinium agent. We have outstanding precision, less gadolinium agent, more precision due to the MRI side of this PET MRI process. So if we co-inject the gadolinium and gallium agents, well, we can measure a change in R1 within the tumor. We can measure the percent injected dose from PET. And then based upon the ratio of the co-injection at the beginning of the study, we can actually estimate the gadolinium concentration. And if we wait for enough agent to accumulate into the tumor, now we get a stable measurement. So we're not using the beginning of the measurement that has less precision due to MRI. And therefore, we can read out a pH value for the tumor. Unfortunately, we do have evidence that the gallium agent is unstable in vivo in this particular formulation, which violates the assumption that the two agents have identical pharmacokinetics and therefore can be compared. So we have switched over to a fluorinated agent, F18, with the gadolinium, and then this F19 atom is not there to perform F19 MRI. Instead, it's there just to ensure the identical pharmacokinetics of these two agents. We then measure the change in R1 due to the gadolinium agent. We measure the activity from the PET agent, and using the initial ratio that was incubated in the tube, we can estimate the gadolinium concentration within the sample. We can combine these results and we can read off pH with our predetermined calibration. Again, the error is on the MRI side of methodology. If we co-inject both agents into a mouse model, we can measure the change in T1 or the relaxation rate. Again, we can estimate gadolinium based on the percent injected dose measured from PET. And if we wait long enough, we get a stable measurement, and our PET MRI pH measurements compare extremely well to a microsensor that we place within the tumor, which clearly is an invasive method. So to summarize, we can measure pH using simultaneous PET MRI. You need a carefully calibrated PET instrument, though. Also, the error is dependent on MRI. We're developing a yttrium chelate as an alternative product because the gallium is unstable. Yttrium should be more stable. We're also improving solubility of our agents. And then finally, I'm excited that we're now converting to performing MR fingerprinting rather than MRI. So we'll be doing PET MRF to improve upon the accuracy and precision of the T1 measurements so that we can get a more accurate pH value at lower concentration of contrast agent. And this is just a corollary experiment where we're doing DCE MR fingerprinting, because clearly the PET MRI that I've been showing is really a DCE MR method combined with the PET so we can track the contrast agent. So with that, I'd like to thank our research group at the MD Anderson Cancer Center. And then also I'd like to thank Alyssa Pollard, a talented graduate student who has since graduated, and she's now a postdoc elsewhere. But we do want to thank her for all her work in championing this project over the years. Thank you.